Hello there and welcome to Upper 6 Further Maths. Here we're looking at multiplying and dividing complex numbers. So let's just see those rules that we need to know for multiplying and dividing complex numbers. If we say we have two complex numbers and we'll call them Z1 for the first complex number equals R1, the first modulus value, e to the theta 1i, and Z2 equals R2 e to the theta 2i. So the 1's here are referring to the first complex number, the 2's here are referring to the second complex number. Then when we multiply these two complex numbers together, you can see what happens here. You take the first one and multiply it by the second one. Now if we were to do this multiplication, then we're going to be multiplying the R values at the front. And then remember, the rules of indices lead us to adding the indices on E. So theta 1i plus theta 2i. And let's just do a bit of factorising in that indice there. You get R1, R2, e to the theta 1 plus theta 2i. So what we're seeing here is that when you multiply two complex numbers together in exponential form, you multiply the moduluses, or the moduluses multiply, and the arguments add. And that makes sense. Moduluses multiply, arguments add. Nice and straightforward there. Division, it's pretty much the exact opposite, as you can imagine. When you divide two complex numbers, you divide them like this, and R1 will be divided by R2, but the rules of indices will lead you to subtract the exponentials, leading you to this equation here. So the moduluses divide and the arguments subtract. So in both the rules, the opposite, the kind of inverse function applies. So the moduluses divide, the argument subtracts. And you might see the rules written like this. If you've got the modulus of ZW, then that's equal to the modulus of Z times the modulus of W. That's exactly what we're saying in this rule here. The moduluses multiply. If you want to find the modulus of ZW, just multiply the individual moduluses. And the same for the arguments. If you want to find the argument of ZW, then just add the two separate arguments and you'll get your answer for the argument of ZW. Exactly the same with the division ones. If you want to find the modulus of Z divided by W, then just divide the two separate moduluses. And with the arguments, if you want to find the argument of Z divided by W, then just do argZ minus argW. So these are the four rules that we need to know for multiplying and dividing complex numbers. For multiplication, it's multiply moduluses and add the arguments. And for division, it's divide the moduluses and subtract the arguments. Let's have a go at a few questions then. So first one is express 2e to the theta, so 2e to the pi by 6i by root 3e to the pi by 3i. So that's this rule here. We're multiplying here, so we'll multiply the moduluses at the front. That will give us 2 root 3, and we'll add the arguments together. Pi by 6 add pi by 3 gives us pi by 2, so it's e to the pi by 2i. These numbers at the front here were multiplied together, but these numbers on the exponentials were added together. And part B, it's a division. Oh, sorry, we're changing this into Cartesian now because it's in the form x plus yi. So it's going to be 2 root 3i. How did I know that that was straight away the answer? Well, I recognised that pi by 2 would lead me to a number that's on the imaginary axis because it's pi round to this other axis over on the left. Pi by 2 would be exactly pointing upwards. Moving on to the next question then, so we're going to be dividing these two complex numbers together, so it's following this set of rules here. Moduluses divide, argument subtract. So 2 divided by root 2, that's root 2, and then subtracting these values from here to here will give you that answer there, and then writing it in exponential form, you get this answer here. Okay, and part C then, quite a difficult question here. We're told that in this question that Z equals 2 plus 2i, the imaginary part of ZW is equal to 0. So when we multiply Z and W together, the imaginary part is 0, or it comes out to be a real answer. And we're told also that the modulus of ZW is equal to 3 times the modulus of Z. use a geometrical reasoning to find the two possibilities for w, giving your answers in exponential form. So, if we're told that z equals 2 plus 2i, we could find the modulus and the argument. So the modulus would be 2 root 2, and we could also work out that the argument of z is pi by 4. Okay, so that's as much as we can do with that bit of information. Let's now move on to maybe the third bit of information. If the modulus of zw is equal to 3 times the modulus of z, then using the rules of multiplying complex numbers, we can split the left-hand side up into the modulus of z times the modulus of w, and cancel out the modulus of z on both sides. So we now know that the modulus of w is 3. So when we're trying to find the two possibilities for w, we know that w is going to have a modulus of 3. And then going to the middle bit of information, if the imaginary part of zw is 0, then the argument of zw is either going to be 0 or pi. And why is that? Well, if we look at the Argand diagram, where we've got the real axis going to the right and the imaginary axis going upwards, then if the imaginary component is 0, that means that we're looking for a coordinate that doesn't either go up or down by anything. It will only go left or right. So in this case here, the argument at this point here is 0. The argument here is 0. Or at this point here, where it's just in the negative real direction, the argument of w is pi. So that's why the argument of zw is either 0 or pi. So what we'll now do is we'll now split this up using the rules of multiplying complex numbers. You can add the arguments separately, so the argument of z plus the argument of w will either equal 0 or pi. We know what the argument of z is, that's pi by 4, so we'll put pi by 4 in here on the left hand side where argument of z is, and then we'll subtract it onto both sides in both of the expressions. So the argument of w is going to be minus pi by 4 when you subtract it from 0, or 3 pi by 4 when you subtract it from pi. So we know from this complex number w that the modulus of it is 3, and the argument of it is either minus pi by 4 or 3 pi by 4. So putting those two things together, we get the complex numbers for w. 3e to the minus pi by 4i, and w equals 3e to the 3 pi by 4i. So yeah, we've done that in exponential form. We've worked out its modulus, we've worked out its arguments, and then just put it in exponential form. So there we are. Sometimes you have to break down the pieces of information you're given in a question, work a few things out with what you can do with that piece of information, and then fit some of the pieces of information together in such a way that will work out a complex number, in this case w. Okay, so that example there was particularly difficult, but all the questions in the exercise aren't that difficult, so maybe let's start on some of the easy ones. Pause the video and give these two questions a go. Okay, these two questions really aren't that difficult, are they really? So we will, in this case, add the arguments together. In both of these two complex numbers together here, the modulus is 1. So it's kind of like 1 times 1 is 1, and then we add the moduluses together, so it's going to be e to the 7 pi by 12i. So that's the answer to part 1a, and on to question 2b. We divide the moduluses by each other, so it's root 3 over 4, and then we subtract the arguments. But in this case, it's a minus, so we're subtracting a negative here, so it's going to be, I don't need a bracket, do I? E, and then we're going to add these arguments together, actually, because one's a double negative. So it's 5 pi by 7. So we've subtracted these two arguments, but because one's a negative, when you subtract a negative, it actually turns into a plus. So it's 3 pi by 7, add 2 pi by 7 is 5 pi by 7. So ignore that start of a bracket there. That's the answer to part 2b. So your turn to have a go at some of these questions from page 7, exercise 1b. Make sure you have a go at this before we move on to the later exercises in the textbook, because it does get pretty difficult later on. It's really important you're good at the basics at this fundamental level. Thanks very much for watching.